Well, hello. Welcome back to POE. Today we're going to talk about Introduction to Electricity. Electricity is the movement of electrons. It's those electrons that, as they're moving, carry a certain amount of charge. It's a little bit like a dump truck. Imagine dump trucks coming up, and they drop off a certain amount of, in that dump truck, maybe they have a certain amount of fuel, and they keep coming. Another dump truck comes and dumps off its fuel, and then the dump truck keeps going. Well, electrons are the same way. They carry with them charge. They come up to an object, they dump off that charge, and then they keep on moving. So it's a little bit of that same concept. Electricity at the atomic level. Well, elements is the simplest form of matter, and here are elements. These are all the different elements. Atoms is the smallest piece of an element containing all of the properties of that element. You can have a big chunk of gold, and that's maybe all of the same element, gold, but within that chunk of gold, you're going to have a lot of little atoms. And but the thing is those atoms, each of them are still gold. They're just the smallest possible piece of gold that you could have. Or it could be silver, or it could be oxygen, or sulfur, or sodium, or anything that's listed up here in the periodic table. Components of an atom. We have the nucleus, the protons, and the neutrons. The nucleus is the thing that's in the center. In that nucleus, we have protons, which are positively charged, and we have the neutrons, which do not have any charge at all. They're neutral, and that's why we call them neutrons. The atomic number, and hopefully this is serving as review, but the atomic number is equal to the number of protons in the nucleus. So if we were to say this right here had, the red ones here are the protons, we would say this has an atomic number of 1, 2, 3, 4. It has an atomic number of 4. And to be honest, we could go back to that periodic table then and say that the element must be beryllium, because it's beryllium that has the atomic number of 4. The atomic number identifies the element. Every element that we come up to that has 4 protons is going to be beryllium. The other ones, these electrons out here, those don't deal with the atomic number. The electrons. Now we're going to talk about the electrons here. Electrons are the negatively charged particles. These are the things that are zipping around the outside, sometimes referred to as the electron cloud out here. But they have orbitals, or we call them shells, or we call them energy levels. But this is where they're going to find the electrons. The thing that's important is the valence electrons. The valence electrons are the number of electrons in the outermost shell of an object. And it's those valence electrons that are key when we're combining chemicals and doing all types of things. And we'll get more detail about those later. But it's the valence electrons that are in the outermost shell, the ones that would be found on the complete outside. Electricity at the atomic level. Well, this is a really big picture here, and it might be a little bit overwhelming, but these energy levels, or these orbits, or these shells, each of them have a certain maximum number of electrons that they can hold. And for example, this is our nucleus in here, and this is our first energy level. It has 2 electrons, and that's because if you look at the periodic table, there are only 1, 2 elements in that first row. What we find out is these shells, or these energy levels, match up to the number of rows. Each shell matches with a row. So for example, 1, 2, 3, 4, 5, 6, 7, 8. By looking at this, this tells me that my second energy level should be able to hold an additional 8 electrons. And as we go here, the second one can hold an additional 8 electrons. The third orbit then tells us that it should be able to hold 10 more Now, and actually this is off here a little bit. This should be 16. The third one should be able to hold 8 more. So I'm going to go ahead and mark that here because some of you may not be listening and just, that should be 16, not 18. Should hold 8 more, which takes it up to 16. The fourth one, then, it tells us would hold 16 more electrons. And our fourth one, so 1, 2, 3, 4. Notice that the electrons got all of a sudden a whole lot closer here. It's going to hold 16 electrons in there, and so forth and so on as we keep going farther and farther through this. Electricity at the atomic level. Electron orbits. Atoms like to have their valence ring either filled or empty. So in this case, copper, in its valence ring, it's got this last ring out here. It's got 1 in it. It doesn't like that. For whatever reason, elements don't like to have just 1 out here. So we would say, how many electrons are in the valence orbit? Well, it's got 1 valence electron. We kind of put it all together as we describe it and say it's got 1 valence electron. Is copper a conductor or an insulator, and why? Well, we say it's a conductor. And the reason we say it's a conductor is because it's going to have this charge out here. What's going to typically happen is it's pretty easy for that one to lose its charge, and that electron can flow very easily. When they talk about in physics and in ICP, we talked about how metals are conductors because they allow the electrons to float freely. This valence electron here is going to be allowed to float pretty freely wherever it wants to go. Kind of combining our POE with physics there. Electricity at the atomic level. How many electrons are in the valence orbit? Well, they show us there's 6 of them here. Right, so that's pretty easy. Is sulfur a conductor or an insulator? Why? Well, it's an insulator. All right, it's got 6, and it's going to be very hard for all these 6, meaning it's not going to allow electrons to flow very easily. It's going to be more likely to take on 2 more electrons than it is to let those go and just start floating all over the place freely all by themselves. Electron flow. An electron from one orbit can knock out an electron from another orbit. When an atom loses an electron, it seeks another to fill the vacancy. So what will happen here is when it loses this electron, it's allowing that to flow. It's knocked out. Electron flow. Electricity is created as electrons collide and transfer from one atom to an atom. In this case, I can't really play this animation, but what you would see here is this electron would leave this one, it would come with this one, it would come around, it would leave this atom, and then go through here. And what we have then is electricity is flowing because these electrons are flowing, in this case, in the example I just showed, from left to right. Because it's very easy for this one to lose it, it's very easy for this one to gain it, and so forth, and so on. So a little bit of notes here about conductors and insulators. Conductors are going to be electrons that have 1 to 3 valence electrons in their outer orbit. Example is going to be most of your metals. Insulators. Electron flow is difficult between atoms, and this is going to be ones that have 5 to 8 valence electrons in outer orbit. Example could be like mica, glass, quartz. Those are all going to be things that have 5 to 8 valence electrons in their outer orbit. Okay, in this example, conductors and insulators. Well, here we have plastics. So these right here, and this plastic over here, these are all insulators. They're going to have 5 to 8 electrons in its outermost shell. And then the metals are where the conductors are. These are all the things that are going to have 1 to 3 electrons, valence electrons, in its outermost shell. Okay, real quickly here, we're going to talk about the electrical circuit. A system of conductors and components forming a complete path for current to travel. Properties of an electric circuit. Well, we have voltage, which is measured in volts, and we have V. Current is measured in amps, and we use an A. Resistance is measured in ohms, and we use this little upside down horseshoe. That's going to be a little bit confusing at first, but you'll come on to it pretty soon. The flow. Quite often we refer to current being just like water. All right. The flow of electric charge is measured in amperes. When a faucet switch is off, just like when a switch is off on the wall, there is no current flow. All right. There's no water coming out of the faucet when it's off. There's no electricity running through the circuit when it's off. When you turn the faucet on, or when you flip the switch on, it allows current to flow. It gives it a clean path, a path for it to go. The water is like a reservoir of water, or the tank or a battery is like a reservoir of water. It's going to allow, it's kind of where we store the water or we store the electrons to make that path. Current circuit. When the switch is off, there is no current. So when it's over here on the left, there's a break. Think of that box right there, that in there, we have this little switch. All right, when it's off, it's here. Here's an incoming wire, and there's the outgoing wire. There's a break right here so that the electrons cannot flow. There's just not going to be any flow. When they move it over here to the on position, this is no longer going to be up there. It's not letting me erase. It's going to be moved from that up position, and it's going to go over here, and it's going to make a connection, and now the electrons can kind of go across that bridge. A switch is a lot like a bridge, I guess you could say. I just kind of came up with that off the top of my head. Next thing we're going to talk about here, conventional current and electron flow. It used to be, before they knew about electrons, and those of you in physics know about this really well, is they assumed it was the protons that were moving. They had to assume something, they just assumed the protons. If I had to guess, probably because they could see the protons and they couldn't see the electrons. So when we talk about conventional current, we talk about how protons would be moving through a wire. And a lot of our math is still derived around conventional current. But we now know that electricity is the flow of electrons. And it's going to be actually in the exact opposite. It's going to go, the electrons are going to be repelled by the negative and attracted to the positive. Just the opposite of what the conventional current is. But still, we quite often talk about conventional current because those rules have existed for so long. Well, I'm going to stop right there at this point, kind of give it a break. And you're going to have a second video that will be a little bit shorter, and we'll give you a chance to watch that. I'll see you on the flip side.